Hello everyone, I'm Zhui from University of Bus, and I'm very happy to be the chair in the last session. And in this part, we have four speakers, Alberto Nardi from IBM, and Ewood Wizards from University of Ghent, Ignacio Badoni from Mano System, and the last will be the Rob Wenderson from UPV. Let's first invite Mr. Alberto Nardi, and his talk will be gallium phosphide photonic crystal cavity for frequency comb generation. Hi, Alberto.
Yeah, can you hear me?
Yes, I can hear you. Please go ahead.
Okay, yes. Can you see my screen?
Yes, I can see your screen and mouse.
Okay, cool. Thank you very much for the introduction, Jiwei. I'm Alberto Nardi from IBM Research Zurich, and as Jiwei just told us, I'll be talking about gallium phosphide photonic crystal cavity for frequency comb generation. So I first want to talk about the outline of my presentation, just to give an idea of what I'll be talking about. First, I want to explain the concept of the device, how we start from a Fabrication resonator and we move to a cavity resonator. So basically the idea of the device. Then I will talk about unit cell bandgap simulations that I've been carrying out during the last few months. And I'll move on to how we actually build a frequency-dependent mirror, and we will analyze different mirror configurations to evaluate the reflectivity of different mirrors. And then I'll just move on to the next steps for, in our research plan for the future. So, as I said, the concept, basically the device is based on a Fabrication resonator. So we have a cavity and two mirrors. The cavity has a length of L and a group index NG. We have an incoming radiation, and basically the coupled light basically depends on the transmission of the mirror, and then the outgoing radiation will be all those frequencies that are resonating in the cavity. Here I wrote the formula to calculate the FSR, and especially just to move on to the actual device that we are trying to work with. So basically, to generate frequency combs, we need an FSR that basically increases with the frequencies. And usually in ring resonators, the length of the cavity is fixed, and we will basically change the FSR in frequency depending on the group index. But we could actually see this problem from a different point of view and actually think, what if we managed to get to fabricate and to use a cavity that changes its length with the frequency? And this is actually what happens for our device. So we start mirrors that basically have a different length for each frequency. So basically, each frequency that is resonating into the cavity will be reflected at a different depth in the mirror, thus having a different optical length in the cavity. So basically, if we manage to fabricate these mirrors that work like this, so basically the lower frequencies will be reflected at deeper points in the mirror, we will manage to get anomalous dispersion by tuning the length of the cavity. This image is taken from this paper from Scott Popp's group in Colorado, and we started the idea to develop our own device. In our case, we are not using external granulation, but actually we are using holes to to produce this mirror. And here I just put a schematic to show you which degrees of freedoms we have. So we actually can work with the lattice parameter A, the radius of the hole, and the waveguide width W. Here I am showing some FEM simulations to show the first two modes that we find in this unit cell. We see on the left the dielectric mode and on the right the air mode. Here the black lines are cut lines, and I plotted on the right with respect to the top view the cross section along this cut line. It's important to say that basically between these two modes, there is actually a band gap in this unit cell. So basically there are frequencies that cannot propagate through the unit cell, and so they will be reflected. And this is basically the idea. Basically the mirror is based on this idea to have this band gap that basically moves such that we are reflecting first the frequencies and then the lower frequencies at a certain depth in the mirror. But then we actually want to be able to modulate this band gap as we like, and it's very important to get a large band gap such that our reflection will be optimal. And to do so, in order to do so, we carried out pairwise parameter simulations. So basically we swept the parameters that we can work with in pairs, and we see how the relative band gap, which is basically the band gap divided by the center frequency of the band gap. Basically, we use these simulations to see how we can modulate the different parameters in order to get a maximum band gap. And you see on the left I have the waveguide width against the lattice parameter, and then in the middle the radius against the waveguide width, and on the right the lattice parameter against the hole radius. And to center the band gap around the 1.55 micrometers, we found out that here these are the parameters that we need to use. Actually, the thickness of the film is a constraint we have because we grow the gallium phosphide layer by MOCVD, so it's not really practical to grow every time a different thickness depending on the particular device that we want to fabricate. So we usually work with 300 nanometer thick gap layer, and with these parameters we achieve a relative band gap of about 20%, which is actually quite good because from the paper I showed you in the beginning, they use silicon nitride and they achieve a relative band gap of about 10 to 15%. So this is actually a larger band gap. And here I'm showing you the band diagram for the structure with maximum band gap. So basically using the parameters that we just found in the previous slide. And this is basically the edge of the Brillouin zone, where pi over a goes from 0.9 up to 1. So at 1, we actually have the band gap. And the blue dots are TE modes and orange dots are TM modes, whereas the green line is the light line. So basically, we don't care about the modes that are above this line. And as we can see, we have a pretty large band gap in the TE mode, which goes from around 213 terahertz, between 213 terahertz and 175 terahertz. Then at some point, we also have a complete band gap because also the TM modes have a band gap around that frequency, but we are mostly interested in the TE band gap. And the pros of this structure are that we have a large relative bandgap and that few modes are actually below the light line. So this is good because we can actually reduce the power that we need for to pump this device. And the main con is that we will probably have challenges in the fabrication because it's not trivial to fabricate narrow holes, both because if we want to make very narrow holes, then it will be a problem to etch all the way down the hole, but also because we are simulating with an oxide cladding, and actually if the hole is pretty narrow, then it might be a problem and we could have like voids in the structure, which would affect the quality factor and the losses that we get out of the device. But a possible future alternative to let's say solve this problem would be to use external crenulation instead of holes. But we have been doing some preliminary simulations, and actually in that case we would solve the problem for the fabrication, but we are having issues with upper modes that basically are coming down, limiting the bandgap. But yeah, so now we are working with holes. And now I want to talk about how we actually build a frequency dependent mirror. So as I said, we want to reflect first the higher frequencies. So we want the center frequency of the bandgap to come from higher frequencies down to lower frequencies as we move in depth in the mirror. And means that basically we want to move to a higher center frequencies to a lower, and at the same time we want to basically to make an adiabatic mirror. We want to come from a situation where the bandgap is very small in the beginning, such that it's similar to the waveguide part that we have in the cavity, and then it becomes larger and larger. So actually what we have to do is something like this. We have to tune the lattice parameter and the hole radius from basically smaller values to higher values, such that in the end we will end up to a point where the relative bandgap is large and the center frequency is the one that we actually want. And this is what we get if we modulate these parameters through the mirror. Basically, the lattice parameter changes from 280 nanometers up to 455. And at the same time, I have to say that the hole radius is changing from 50 nanometers to 165. And this is actually how the edge of the brilliance zone looks like. So now we are at pi over a equal to 1. Basically, this is the bandgap. And the blue dots are the lower band, the orange dots are the upper band, and the second upper band is the green one, which is fairly above the other two bands. So, and we see that, yeah, we are reflecting first the higher frequencies and then the lower frequencies. So we can build a mirror like this. And here we see different configurations. Basically, we are adding a constant parameter holes in the beginning just to make sure that the reflectivity is fine, and then the linearly tapered part just to reflect first the higher frequencies and then the lower frequencies. And you can see the number one has tapered part that has 10 holes, then the second one is very small, it has 2 constant holes and 5 tapered holes, and the last one has still 4 constant holes like the first one, but a much longer tapered part. And as you can see on the right, the short mirror has worse reflectivity compared to the other one. Basically, we are measuring the power that is reflected, that basically comes back at this port. I don't know if you can see my mouse, but I think so. So basically, we introduce the light from this side and we measure what we get back. And yeah, we see that the two long mirrors are quite good. They're both kind of comparable in the middle of the band gap, but the longest one basically has a wider frequency range with a good reflectivity. Right now, we have to move on to study the dispersion compensation as a function of the geometry, so that we can tune the dispersion from anomalous to normal as we want. Then we would have to solve the Lujat-Lefebvre equation to study the frequency comb generation. Then we fabricate devices and measure. And at the same time, we have already started this, but we would go on with the simulation of photonic crystals with external granulation instead of holes, just to have an alternative for the problem about the fabrication. And this is all from my side. I would be glad to answer questions if anyone has any.
Okay, thank you, Alberto. Is there any questions for Alberto, please? Okay, okay, please, Dimitri.
Yes, Alberto, thank you very much for the interesting presentation. So what are your expectations in terms of the comb characteristics, like free spectral range, quality factor, all these important parameters? How many lines do you expect to get?
I mean, the free spectral range, it will basically depend mainly on the length of the wavelength of the waveguide that we have in between the two mirrors. So that will be the main parameter to choose to tune the free spectral range. And then depending on how big is the normal dispersion that the waveguide is introducing in the device, we would have to tune the mirrors such that they are compensating just that normal dispersion with their anomalous component.
But do you expect to get any advantages over the devices? What type of kind of?
We are developing this kind of devices to basically limit the power threshold, because given that these devices are smaller than ring resonators, then we would have a lower effective mode area, and then the power would be much lower. This is basically the main thing.
But this will compete with fineness. It's not only the volume is important, right? It's
yeah.
Actual fineness provides the enhancement.
Yeah, the mirror is actually very important. Is the main component of this device that is actually limiting everything. If you get to depending on what kind of mirror you are developing. So basically, if it's too short, then it won't be adiabatic and the finesse will be smaller, and because you would have much more losses. But if you have a mirror that is like long enough, then it is adiabatic and the losses should be quite small, and so we would have a high finesse. The trade-off is basically that since if we want to couple the cavity passing through the mirror, the good thing about the finesse that would have a long mirror is actually a problem, because then the transmission through the mirror to couple into the cavity would be lower, and so the cavity would be undercoupled. But to solve that, we could actually couple the cavity evanescently, like we do with the rings with an external waveguide. So there are many possibilities to work with this device.
Okay, thank you very much. Thank you. Very good, very interesting.
Thank you.
Okay, thank you. And we have a last question from Ewood.
Yeah.
Yeah, I was wondering, I'll make it a short one. I don't know much about photonic crystal waveguides, but I would expect that if you zoom in the sweeps that we saw of your wavelength to transmission, they are quite coarse. But I would expect that if you zoom in a bit on this, that you would start seeing steps because of the discreteness, sort of your holes being somewhere. Is this actually correct?
Talking about this.
Yeah, so here your frequency spacing is like 2 terahertz or something.
Yes, exactly.
Would you expect, if you go to a finer resolution, that you would start seeing a staircase effect because of when it starts to feel the hole, sort of?
Yeah, it could be. I mean, right now, like we are trying to limit the simulation times, so we are not using waveguides that are too long. But if we use, I mean, in the end, we would have to use like waveguides that are like hundreds of micrometers long. So the spectral range would be much smaller than this, and we will have many more resonances. But for sure, the problem of having a mirror that is discrete, it will always be there. So it will be a trade-off at some point with having between having, you know, low losses, so not a too small mirror, but not even and like, you know, the longest the mirror, the finest is the tuning between each hole. So, but at the same time, that would be a problem for the transmission. So maybe if we couple evanescently, we can get to a, you know, to a finest tuning of every parameter, but this is still, we have to get to that point.
All right.
Okay, I'm sorry, I need to interrupt you. Maybe you can discuss after this talk.
Yeah,
a little behind time. So next one is you. Yeah, please introduce your talk. And the title is Bot Coupled External Cavity Model Locked Lasers. Yes, please.
Yes. Now I see my red bar.
Yeah, now it's fine.
All right, perfect. So my name is Ewout. I'm from the University of Ghent, and I will present about my first working results with bot-coupled external cavity mode-locked lasers. So I'll first quickly go over what I'm trying to do again, just like in the last presentation. So I'm trying to generate an optical frequency comb that will be useful for dual comb spectroscopy, where you take 2 frequency combs with a slightly different repetition rate, and one of those you send through a sample. And then using a single detector, you can retrieve the absorption spectrum of the sample using only one photodetector and one RF detector. And the way I'm gonna do this is by using bot coupling, where we have 2 different chips, the gain chip or reflective semiconductor optical amplifier in orange in this case, and then we're gonna have an extended cavity that's built on a silicon nitride chip, which is in this case in blue. And then we use the silicon nitride as an extended cavity on a different chip, because when we try and do this on the same chip as the RSOA, we'll have to use an active material if we're not going to do anything like transfer printing. And then active materials always have quite lossy waveguides, and this would then deteriorate the performance of your extended cavity laser. So I have gotten quite a large collection of gain chips right now, and I, for example, tried to get it working with the HHI gain chip, but the results weren't very promising. The same thing with the 1180 nanometer InnoLume quantum dot gain chip, but today I have results that do work using the gain chip I made in MPW run. So the first thing I tried is by just using a silicon nitride waveguide that was air-clad, since the oxide claddings in our clean room are quite lossy. According to the simulation, this would give a theoretical coupling loss between the gain chip and the cavity chip of 3 dBs, but actually we got 6 dBs when I measured this, and this was too much loss to get the mode lock laser working. I could get some lasing, but there was no region in which I would get mode locking. So I improved the design of the edge coupler by having an intermediate waveguide in SU8, which is a polymer with an index of 1.54, I believe. And since it's a polymer, we spin it onto our sample, and we can actually match the height of our mode as well between the silicon nitride chip and the gain chip. But the trade-off is that we do get an extra loss because we have to couple from the SU8 to the silicon nitride waveguide. But then theoretically we would get around 1 dB loss, and if we measured this to a fiber, it was 2 to 3 dBs of loss. So we have less loss, and also we're less sensitive to the vertical alignment since our mode is a lot larger in that direction. So I expect this will work a lot better. So to actually show which cavity and RSOA we're using right now, on the smart chip we have several types of RSOAs. We have a few short gain sections of 850 microns with 2 different absorber lengths, and we also have a longer one, and we're trying to do some things with another, so not a Fabrication mode lock laser, but a ring type mode lock laser. But we're not using those today. We're only looking at one combination where we have the 850 microns gain section, then a 50 micron absorber section, and then we're adding 2 millimeters of external cavity in silicon nitride. And the reflector that was on our sample turned out to be a 65% reflector. So the first thing I tried was to see if I actually got lasing by seeing what the LI curves looked like. And I did this for several reverse absorber biases. And we got exactly what you would expect, that the laser threshold here increases for a decreasing absorber bias, which makes sense since if you add more bias to your absorber, it will relax faster, and therefore it can absorb more photons over the same amount of time. So you'll have to compensate for this with extra gain in order to still start lasing. And we also saw that the saturation power was around 0.35 milliwatts. And this was outcoupled into the fiber. So then I tried to look for regions in which I actually found mode locking by taking the output signal of the laser and shining this onto an RF photodiode and seeing whether I saw beat nodes on an electrical spectrum analyzer. And you can see on the left that there's a very large region where we get a RF beat node at the frequency that we expected, around 15 gigahertz. In this case, it was 15.5 gigahertz. And the region where we get mode locking is very large, and the optical output powers also don't vary a lot. You can see there's one measurement error here, and then the rest, there's a variation of mostly 1.5 decibels. So then I also started to check in which operator we small line width. In here, it's actually the region where we have no power in the RF beat node. So we're not gonna look at this. And then there were only 2 regions that had a small line width, and they were both near a gain current of 140 milliamps. And it turned out to be that here in this region, at -2 volts, 140 milliamps, we get the lowest RF line widths. So that's what we assume to be the optimal operating point of this laser. And then if we take a look at the optical spectrum at this operating point, you will see that it's quite broad. I would call this the spectrum of the pulse. And you see that the 10 dB bandwidth is around 5 nanometers, and the 3 dB bandwidth is 1.5-ish. And the mode spacing is, of course, the 15.5 gigahertz. That's the rep rate of our laser. I then took traces and a autocorrelation trace as well. And you can see that if we make a void fit of this RF peak zoom, we get a minus 10 dB bandwidth of around 1 megahertz. And if we take an autocorrelation trace, we fit a pulse width of 4.7 picoseconds. And this makes, if we compare this to another publication, I only recently saw this, so I've not added it yet to the presentation, but I can link that later on if people want. There was another laser that was made in the same platform, also in the smart platform, but this didn't use an external cavity on a different chip, but they kept it on the same chip. And since the cavity is not very long, it's only 2 millimeters, the losses in my cavity and the cavity in that publication are actually very similar, but there all the loss is in waveguide losses. Well, for me, all the loss is in edge coupling losses. And then the RF peak width is almost the same. So we're reaching almost similar performance, which makes sense. But we are doing it with an extra chip instead of doing it on the same chip. So these were my results for now. Thanks a lot for listening. If there's any questions, feel free to ask them.
Thank you, Ehud. Yes, there's a question from Ro. Yes, please.
Hi, about this rule. Thank you for your presentation. I have a question about the spin coating of the SU8. Like, how do you do that? Do you do that on a wafer and then pattern it, or make sure it's only the interface?
Yeah, so in our clean room, we never really work wafer size. We always do everything at a sample scale. So the process flow I've used is that I take a silicon nitride on oxide wafer. I cleave this into pieces. Then on a single piece, I spin E-beam resist. Using the E-beam, I pattern my waveguides. Then the waveguides for silicon nitride have a single edge depth. So that's a very simple one litho, one edge process. When that is done, I take my sample and on a spin coater, I spin coat SU8. And since SU8 is a photoresist, I then directly expose my waveguides into the photoresist. If I then develop and bake, the photoresist will stay there, and that will be my waveguide.
Okay, thank you. I didn't know that SU8 was a photoresist as well.
Ah, yeah. It's a very nice material, I think.
Okay, thank you.
Okay, thank you both of you for the talk and questions. I think we should move on to the next one. Mr. Ignacio Bodoni from Mano System, and his talk is about microresonators for radar and astronomy applications.
My name is Ignacio Baldoni. I am working at Mano Systems, and the presentation that I will give in today is about applications for silicon nitride microresonators, especially into radar and astronomical fields. So, as you may know, the advantages that silicon nitride provides in matters of photonic integrated circuits are several. Here I listed a couple, which are a small footprint. We have lower power consumption, reduction in the usual propagation losses, even a reduction in cost, among several others. And that's why these are the reasons why here at Menlo have started to work with this platform, in particular with two main collaborations with Licentech and EPFL. EPFL guys are the ones who are providing it at this moment, the chips, the microresonators that we're working with. And we have two main approaches. First of all, to explore the phase noise properties for radar applications. And a second one, more complex, is the reduction in the cost, the size, and also in the complexity of our current calibration for astronomical spectrographs systems, also known as astrocombs. Moreover, what we want to accomplish with all this is to expand the market to other spectrographs, to other types of spectrographs, and eventually we would also like to send this to space, given that Menlo already has some experience on this field. So the first project is this ultra-low microwave generation for radar, in which the state of the art, the motivation of all this project is that in the heart of every radar system, we want a low noise microwave source. The reason why we want low noise is because obviously noise will limit the visibility, the range, and also the resolution of the radar. So what we are trying to accomplish in this project is to build a photonic microwave source, which is not usual, given that everything is always an all-electronic solution. We want to build a compact, small, and robust system that can also be suitable for challenging environments as vibrations or temperature, among others. Obviously, we have in mind the concept of this economy of scale to make a cheap type mass production. And also, obviously, we would like to improve the performance of radar to overcome these issues that I was mentioning before, which are visibility, range, and resolution. So, just to make a short overview of what we are trying to accomplish, first of all, we want to have a frequency of 12 gigahertz. This is in the radar wavelength. Volume of the optical components of 50 cubic centimeters, which is this will include the laser, the modulator, resonator, obviously, among photodetector as well. And the most important concept is the phase noise that we want to accomplish here is minus 150 dBc over hertz at 10 kilohertz. In case you are not familiar with the concept of phase noise, I made a short graph where I show what is the results to date in the moment that this project began, which is last year. And where are we trying to go? If you see here, this project wants to accomplish minus 150 dBc over hertz at 10 kilohertz, and the usual values are around 20 dBc higher. So even though we may not accomplish this minus 150 dBc, it would also be to be lower. It would be also very good. So the system layout, unfortunately, I had this here. Okay. The system layout is, I made a short scheme here of what is it about. We have a CW laser, which is chip-based, which will pump a 1542 nanometers wavelength. This is the usual telecommunications wavelength that will go through an EDFA, and it will pump into a microresonator in order to generate a solitonic comb. Here we have two DWDMs. The first one will take care of getting rid of the amplified spontaneous emission coming from the EDFA. And the second one will be for filtering the signal that we want to get, the microwave signal. And the second one for the PDA, for generating the error signal that we will establish into a pound driver Hall lock. And this is also the reason why we have an EOM in order to get the sidebands for the PDH. So the first concept that we did was to work with a 20 gigahertz chip package here at Mello. The package was done into a butterfly package, also working with PM lens fibers. All this system is PM. And we were able to accomplish 8% of through coupling efficiency, which is not that much. With a EDFA pump power of 325 milliwatts, we were able to get, well, sorry, this was not going to be this way. We were able to get a nice solitonic comb, but this is not the repetition rate that we want to work with. It's 12. But anyway, as a proof of concept, we also got a microwave signal, which is the signal that we have here. And this was done in particular with a high order soliton, locked also through a PDH lock. But in this case, we didn't care too much about reducing the phase noise. We only wanted to prove that we can create the microwave signal, generate the microwave signal. So in this concept, in this experiment, we work with a noisy microwave amplifier with a noise figure of around 5 dB at 20 gigahertz. So anyway, we keep going, and now we have started to work with a 12 gigahertz chip. And not long ago, we were able to get a single soliton comb generation at 12 gigahertz. This was done thanks to a higher through coupling efficiency of around 23%, and even a lower EDFA pump power of 250 milliwatts. Moreover, what's very exciting is that we could self-lock this comb at least for 10 minutes without the need of any PDH, even though we may need it for a full stabilization. This is very good also because we can work without having to establish all this equipment, which is rather complex also. So now in this particular project, the next and final steps are to make a full phase noise characterization of this solitonic comb with Mello optical cavities. We want to characterize and also optimize the RF power that will come out from this microwave signal. And unfortunately not this year, but probably at the beginning of next year, we were able to perform some cross-correlation measurements to reduce the noise coming from the instruments and have a more intrinsic knowledge of the comb itself. So in this project we have, learned a lot about this kind of systems, and now we will go into a much more complex scheme, which is the calibration of spectrographs using microcombs. So in this project, the motivation of it is that Mello has what is called the Astrocomb, as I mentioned before, which is a device that will calibrate the astronomical spectrographs will provide a calibration of even over years that will allow the detection of extrasolar, that would allow the detection of extrasolar Earth, the acceleration of cosmic expansion, variation of fundamental constants, among others. The problem of this concept is that it's rather complex. Here is a picture of the Mello Astrocomb installed at ESO in Chile with the ESO collaboration. And the system is, as I said, very complex. We have 3 Fabry-Perot cavities that need to be locked all at the same time. And after that, we even have to work with a power amplifier, a pulse compression, spectral broadening, among other difficulties. But the what we are trying to accomplish in this project with the microcomb is to replace all these Fabry-Perot cavities locking with an entire microcomb system. So this, in principle, would be able to get rid of an entire rack, and if we keep moving forward, even more. So the main goal of this project is to integrate 25 or 50 gigahertz microresonator into this system to reduce the astrocombs complexity, size, and cost, and even improve the performance of it. We have some challenges, obviously, which is that we are going to start working at 1050 as a critical, and this is a critical wavelength. It's not the usual 1550 nanometers for the microresonators, and this wavelength has obviously a small mode diameter, which will can create many issues with the fabrication precision, also to generate and lock the single soliton, which is also very important for us to accomplish. And moreover, in the spectral broadening, we have to work with PCF, with photonic crystal fibers, whose lifetime might be compromised due to the high repetition rate. The higher the repetition rate, the more power you need, and the PCF can degrade faster. So these are the challenges that we will have to overcome in this project. So far, the work done is we have made alongside EPFL some simulations to prove that pulse formation and sufficient through-coupling efficiency is possible. And with all this, we could finish the entire conceptual design of the project. And while the photolithography masks were designed and the chips were fabricated, we improved our chip packaging techniques, and obviously we bought the entire equipment that we need for go on with this project. And in particular, last week we got the first generation chips. So the short-term goals for this project is to make a completely microresonator characterization, and also we would like to at least be able to generate a fundamental soliton at this particular wavelength, and in a larger time frame make the entire packaging and also a lock of the system. So that would be all from my side. Sorry for the inconvenience with my computer.
Okay, thank you for your presentation. It's a great talk. Is there any questions for Ignacio? Please raise your hand. We have time for one question. Okay, if no, then I think we can move on to the next one. Maybe Ro from UPB, and his talk will be the design of a spectral processor.
Okay, so welcome to my presentation. We will continue with or finalize with a linear device to ease off. So I will talk about a spectral processor, and we already saw the spectral processor very briefly in the talk of my professor, but I will repeat the idea. So what we have here is a comp input. Then the comp lines get demuxed at the AWG, and the different channels will be phase and amplitude controlled by Mach-Zenders, and then muxed again in the second AWG, and then they can be sent to, for example, a photodetector in order to create a high frequency signal. So because I don't yet have any chips produced, I will talk to you about how to design such a device and what design considerations I took into mind. And interesting to tell that I also defined the whole PDK with automatic building blocks for example, the AWG in order to be easily transferred to a different platform. So we will talk about the AWG, the Mach Zenders very briefly, and then the layout structures that are possible. So first, the AWG, I will guide you through the working principle. So light gets sent into at one into a slab coupler. Then this light is broadened and sent into the array of waveguides. And in the second slab coupler, constructive interference will happen at a different output ports because the path lengths that the array of waveguides in 3 are different. The construction will happen at different places for different wavelengths due to the amount of wavelength that fit as it fit into this path length. And then you will have a demultiplexed array of signals. So as you see, the path length is very important, and also the path length is defined by an integer number of wavelengths. So every path is 1 times m longer than the previous, and m defines the free spectral range in an AWG. On the right-hand side, you see how you can calculate the path length. This is basic Tory geometry. So I will not go into much detail for this one, but if you're interested, I can share you any considerations, etc. It's important to note that the path length should be into account that it should be taken into account that the different refractive indices for a band or a straight path are taken into account. So I defined this as if effective length, which is the path length times the effective index. And I did this for 3 different design strategies. So another constant radius design where we only have 1 band, and then a variable radius, which is also a kind of the mind layout for a mind-Smith layout for the AWG. There it's important to take into account the different effective index for every different band, and it can give slight performance improvement because you can use bigger radiuses. So then if we define all the path lengths, we should define where to put the ports. I did this by simulation. It can also be done analytically or mathematically with basic formulas used for AWGs you can find in literature. But because we have a very precise input, I wanted to simulate the whole AWG to be sure that the ports are placed exactly there where the comp line will be present. So I simulated the AWG for every wavelength of interest, and then looked at where the power output will be highest. I did simulate the AWG as a mathematical model, so I took into account how much the beam spreads into the slab waveguide, and then the phase differences along the whole path in order to see where the recombination of light happens. Then I took one layout to continue with. That's the orthogonal layout. I took this one because it's least constrained in terms of dimensions. You can basically add as many paths in the array of waveguides as you want without running into overlapping paths, etc. And also, we will produce the first chip in an E-beam technology, where the stitching errors can now be defined in just one direction instead of in diagonal waveguides. Also, this layout tends to give a very small footprint because of its longitudinal shape. Interesting to tell is that I also took the mounting proposal of Zhu, to give a performance improvement. As you see on the right lower picture, there are two different ways to define the difference in distance between the array waveguides. So you can define them along the grating circle, or you can define them along a tangent line equal in distance. The second way of defining them gives a great improvement in the sideband of the output signal. So I would highly recommend, if you ever define AWG, take a look at this. So let's continue with the design that I chose for. This is a 9-channel AWG with 100 GHz channel spacing. As you see, there's a suppression of roughly 35 dBs of the next, say, comp line, if you use a comp as input, or minus 15 dB in the direct overlap of the channel. Then the next thing we need is the Mach Zehnder. I will go very briefly through this one because I think it's quite commonly known. I chose a 1x1 design because in the spectral processor we only want to have one input and one output of the phase control. I also used the balanced path lengths, so equal path lengths, because that saves both space and gives an equal response over wavelength. Then the tuner length I chose is 1.5 millimeter. That's quite long, and that should at least be sufficient. I try to define tuners that are proven and not went into much detail to improve their performance. So then the layout. Once again, the picture of a spectral processor. So as you see, we need to have one AWG to demux and one to mux again after the array of Mach Zehnder's. Now this can also be done in a different way with a loopback structure, where you guide the waveguide back into the same AWG. But let's first discuss the idea with two AWGs. So in this way, you have a very straightforward way of connecting everything, and also it can be easily the path lengths of all the paths can be matched to be sure that coherence is kept. There's one problem, that's that the two AWGs need to be matched. So due to imperfections, we should solve this with at least one thermal path on the AWG. And also this strategy takes up quite some space. So a second idea is to wait 1 second. This is the response you would get from at the left from the first output of the AWG, and then on the right side you see what you would get if you then combine them again. So you see that all signals are combined again at port 0, the middle port. So that's desired. The other ports are not as interesting because you will not have a look at them. Then the other way to connect everything. So you send the signal into one AWG and then redirect all the channels but one back into the input slab coupler of the AWG. This has two main benefits. That it's space efficient, and also because you use the same AWG, there's no matching problem. One downside is that you lose the control of the in and output channel, because you cannot add a Mach Zehnder interferometer in there, because you would then control all the channels. Also, because of this circular loop, it's quite hard to match the path length. You would need to use spiral structures in order to do that. The spectral response of this would look like this. So In this case, we use one of the side channels, so you see that the spectral response is shifted, and the central wavelength is now guided to one of the side ports. And then the signals are all recombined again at the input port, respectively. Okay. Then, because we lost the control of one port, I also thought of another way to define a AWG. So here I added like an extra, or well, I placed the central port at half a channel spacing in order to free it of a comp line. So then we could align a comp to all the other in and output ports of the AWG, and use the central port just for in and output of light and not for a comp line. This idea is favorable in terms of controllability, but it consumes a lot of space because you need a bigger AWG to support the extra channel. And then to conclude, this is the basic layout of such a processor. So as you can see, there's the AWG. The light gets split into the Mach-Zehnder interferometers with their thermal tuners, and then redirected again into the AWG, and then the combined signal is sent to the output. That's my my presentation. If there are any questions, this is the time.
Thank you, Ro. Is there any question for Ro? Okay, so maybe I will have one. I think your design is very great, but have you tested it in the fabrication or experiment? I've seen all these data from your slides have a lot of performance, right? Is it purely, you know, done by the numerics or?
Yes.
Right.
So as I said, I did not yet fabricate any chips. So this is all still modeled and also mathematical models without taking into account any losses, because we don't know the waveguide properties. So yes, I'm very excited to finalize my layout and have a first chip to see whether the models match the actual performance.
Okay, great. Okay, I think we are here, and thank you all these talks. And Joanna, maybe you have something to say, please, Joanna.
Yes. Yeah, thank you very much to all ESRs who've taken part in today's webinar. I'm sure that everybody found it very interesting, and it's good to see the progression you've made. And I'm sure that you can see the progression you've made since the first ESR webinar back in April. We'll continue with webinars, as I said last time, in the next year. And we warmly invite everybody to attend a webinar on the 18th of January. I will send invitations to this webinar shortly. The speaker of that webinar on the 18th of January will be Professor Derek Reed from Heriot-Watt University in Edinburgh, so you're welcome to see his profile and to attend the webinar. Moreover, thank you very much to all the chairs, Professor Scriabin and of course our ESRs who agreed to chair session 2 and session 3, Mikhail and Jue. That was a good experience for you, I guess. And we will welcome you after the Christmas break. So have a good Christmas, take care, and we'll see you in the new year.
Thank you, John. Thank you. Goodbye.
Thanks.
Thank you. Bye.
Thank you. Goodbye, guys.
Thank you. Bye.
Bye.
Guys.